Hello everyone. So let's talk a bit about perfect rolling. And remember, perfect rolling means that there's no sliding going on at the contact point. So let's say that this object here is a disk and it's rolling without slipping with a uniform acceleration, right? Which would look something like this. Note that most points both rotate and move linearly, but the center of mass only moves linearly with a constant acceleration we shall call a cm. Right? Cm stands for the center of mass. Watch it one more time. There we go. Well, we can relate these things to one another, as we've done earlier. Right? Remember that if this is the distance a point on the outside has rotated through, the arc length of it, if you will, and this is the distance of the center of mass, remember that those are related. We drop a little vertical here. This is the angle it's rotated through, right? The angular displacement of it as it's rolled. This, of course, is the arc length. Right? And we found in the past that the arc length that a point on the outside moves through is the same as the distance the center of mass moves. And therefore, we can relate the distance the center of mass moves to the angular displacement and the radius. And we can do a similar kind of thing with the velocity of the center of mass and with the acceleration of the center of mass. Because if this thing is going to roll without slipping, the center of mass and this point on the outside have to have the same, have to move the same linear distance with the same linear velocity and the same linear acceleration. Otherwise, it would slip, right, on the ground. And we're not doing that. We're rolling without slipping. So as we did here, some proofs along the way, we can relate the distance the center of mass works to the angular displacement and the radius. The speed of the center of mass is equal to omega r, or the angular velocity of the rotating object times the radius. And the acceleration of the center of mass is equal to the angular acceleration alpha, that's an alpha, right, times the radius. And you can look back at prior videos, right, if you want to see those derived. Okay? Remember that we have to do these in radian measure for the units to work out. Radians, which are really not a unit, but more of a name. And we call this the rolling condition. Right? These things have to be true for an object to roll without slipping. Okay? The outside of the rolling object has to have, or must move, through the same distance as the center of mass with the same linear velocity and the same linear acceleration. Otherwise, it would slip on the surface. So what does that do for us? Well, it allows us to think about rolling here in a little different way. Perhaps we can look at rolling as a combination of purely rotating and purely translation. Pure translation means purely moving linearly. Okay, and if we put those two things together, we get perfect rolling. So from the standpoint of pure rotation, say this object is, therefore, we're just going to look at the rotation of the rolling object, right? And it is rotating with an angular velocity we will call omega. And in the picture, it was the previous slide, it was rotating clockwise. Well, in this case, if we're looking at it as pure rotation, the center of mass isn't moving at all. But a point on the top, we can relate the speed of the center of mass to omega and r. And so that means that the top would be moving forward with a speed of the center of mass, because it's a distance r away. And a point on the bottom would be moving backwards with the speed of the center of mass, because again, it's a distance r away. This is looking at the rolling, but just the pure rotation aspect of it. Now, if we add to that the pure translation, the linear motion of it, when we look at something and we just say, oh, it's moving linearly, which we did all last year, right? We just deal with and say that the entire object is moving with the same speed. So if the center of mass is moving to the right with a speed we will call VCM, So is the top and the bottom. Right? The whole object is moving together, right, with that speed. But here comes the cool part. What happens if we combine these? Well, then we get rolling, right? So the center of mass isn't moving at all for pure rotation. Translationally, it's moving with the speed of the center of mass. You add those up. The center of mass, of course, moves with the speed of the center of mass. That kind of makes sense, right? That's what we call perfect rolling. However, look at what happens at the top and the bottom. At the top, because it's rotating, the topmost point is moving to the right with the speed of the center of mass. Because it's also moving linearly, the top is moving to the right with the speed of the center of mass. So you put those two together, and the top is actually moving at twice the speed of the center of mass. Interesting. Half of it is because it's rotating, and half of it is because it's moving translationally or linearly. But look at the bottom. This one's even weirder. Because of the rotation, the bottom is moving to the left with the speed of the center of mass. But in terms of its pure translation, it's moving to the right with the speed of the center of mass. And you add those up, and what do you get? You get 0. Which means that a point on the bottom of a perfectly rolling object isn't in motion with respect to the ground. Right? A point on the bottom is not in motion with respect to the ground. Right? If it was, it would be slipping or sliding across the ground. Now that may seem like a strange idea, right? That the top part is moving twice the speed of the center of mass. The center of mass is, of course, moving at the speed of the center of mass, and the bottom is not moving at all with respect to the ground. But take a look at this picture, which I pulled out of your book. This is a bicycle wheel rolling from left to right, perfectly rolling from left to right at a constant speed. Look at the picture. When you take a picture of something and it's blurry, what does that mean? That means it's moving. The blurrier it is, the faster it must be moving. Well, look where this is the blurriest, right? At the top, which is where it's moving the fastest. And it gets less blurry as you move down, but look at the very bottom, where the picture is essentially clear. Why? Because it's not moving with respect to the ground, which is the frame of reference of the camera. So with respect to the camera, the bottom of this perfectly rolling wheel is not moving with respect to the camera, and therefore is not blurry at all. Kind of interesting, right? I mean, this is a real picture of a bicycle wheel rolling. Now, the thing about not moving with respect to the ground means that at best there would be static friction, perhaps, depending on the situation that we'll discuss, right, between the surface of the wheel, let's say, and the ground. And static friction doesn't dissipate any energy. Right? You don't get any heat generated, any thermal energy stored from static friction. You got to have movement, sliding of the surfaces in order to change that temperature, right? Store that thermal energy. So static friction doesn't dissipate any energy. There'd be no E-dis with perfect rolling. Only if the surface slides as it rolls. Okay? Now you might be asking yourself, well, hang on a minute then. Why does a rolling object even ever stop? Right? If it's rolling perfectly and not slipping, why does it eventually roll to a stop? Well, there's another kind of friction that we haven't really talked about, and we're not really going to talk about it much except for right here. We're not going to calculate it. It's something that we're going to be able to ignore for perfect rolling. It's something called rolling friction. Okay? Rolling friction is something that occurs when you have a rolling object, right? And it comes from two places. One is losses of pieces of the object, which dissipates some energy, right? Think of a car tire or a bike tire. Over time, what happens? Well, it wears through the tread, right? Well, where did that tread go? It didn't just disappear. It got literally ripped off of the bottom of the tire. And that dissipates some energy. But perhaps the biggest piece of rolling friction is what happens to an object as it rolls. What happens to the bottom of the object? It deforms. Think of a car tire. Go out and look at the car tire on your car when you go home tonight. It is not perfectly round. It is flat at the bottom. Right? There's a little flat piece. But it doesn't stay flat as it rotates or rolls. As that point moves up to the side, it pops back out again and goes back to round. Well, anytime you deform an object, right, and then it goes back to its original shape, you're going to dissipate some energy. There's going to be an increase in the temperature of the tire and the ground. Now, the more solid the object is and the more solid the ground is, right, the less rolling friction there would be. But you can never get perfectly solid, right? Even if it's a hard object and a hard floor, if you look at it microscopically, there'll still be some deformation at the points of contact. But like I said, we're basically going to ignore rolling friction when we talk about perfect rolling. So consider a disc that's rolling at constant speed. Because it's already rolling at constant speed, there's no tendency for it to slip, right, at its point of contact with the floor. And if there's no tendency to slip, well, then there's no frictional force acting on it. So the force diagram, extended, becomes a force of gravity acting at the center of gravity, which would be right in the center, which is the axis of rotation, and a normal force acting from the point of contact with the surface, right, because that's where it's being supported. And those two forces would, of course, have to balance because the object isn't even moving up and down, much less even horizontally, it's only moving at constant speed. And notice that both of these forces act through the axis of rotation, and that means they exert no torque. Since there's no torque acting on it, it can't change its angular velocity. So it rolls constantly. The center of mass moves at a constant linear speed, and the object rotates at a constant angular velocity. However, if you do apply some sort of force on the disc, like say if you're riding a bike and you push on the bike pedal, which puts a force on the bike through the axle and all of that kind of stuff, then there's a tendency for the point of contact to slip backwards, right, on the ground. Think about if you try to ride your bike and you try to get going and you're on gravel, right? It shoots the gravel backwards when you get going, right? And that's because that point is slipping on the ground at that point. And then friction applies a force forward, Newton's third law, which applies a torque because it's being applied at the outside of the rolling object, and that torque causes an angular acceleration. And so away it goes. And so then it ends up, the rolling object accelerates linearly and rotationally. The speed of the center of mass changes, and the angular velocity changes. Now, if it's perfectly rolling, this would be a static friction force, right? Because then the bottom doesn't slip with respect to the ground. And if it's static friction, it doesn't dissipate any energy along the way. Now, let's talk about that energy that it has, and in particular, the kinetic energy of a perfectly rolling object. Well, we said a moment ago that we can treat rolling as if it is the sum of perfect rotation, pure rotation, and pure translation, linear motion. We can do the same thing with the kinetic energy. So when something is rolling, it is both rotating and moving linearly. And therefore, its kinetic energy has a rotational part and a translational part. We already know how to calculate those two things, right? The kinetic energy of rotation is 1/2 I omega squared. And for a rolling object, right, the I is around the center of mass, right, because a rolling object would rotate around its center of mass. And the kinetic energy of translation is the old friend 1/2 mv squared that we used before, where technically this is the speed of the center of mass, right, is what this v is. Now, these may look like things that can't be put together, but they can, right, with some conversions of what I is, the rotational inertia, and the angular velocity, as you'll see here in a little example we're going to do. But you need to remember that when something's rolling, its kinetic energy has two parts, and you have to use both parts. It's a very common error to look at something that's rolling and only look at its rotation or only look at its translation. But remember, it's doing both. Right? So our kinetic energy has two parts to it. This is the part due to rotation, and this is the part due to translation, or the linear motion of it. So let's do a little example. Say we've got a small hoop of radius 14 centimeters and mass of 2 kilograms, and it's rolling across a table with a constant speed of 0.1 meters per second. We have to assume here it is perfectly rolling. I want to know, what is the kinetic energy of the hoop? Well, as we just discussed, the kinetic energy of the hoop is going to have rotational and translational parts. Looks like we can't put these together, but there are some changes we can make. For example, we can rewrite the angular velocity in terms of the velocity, or the speed, of the center of mass, because we know the speed of the center of mass is omega times r. Right? This omega is the angular velocity that it's rolling with. So that means omega can be written as the speed of the center of mass over the radius. And by the way, again, this speed of the center of mass is what we're calling this v. That v is the speed of the center of mass. It's kind of traditional in these to just write it as v, but technically I like to write it this way here before we make the substitution so that you can see where it's coming from. Now, we need to convert it because we weren't given the angular velocity, we were given the linear speed. If we were given the angular velocity, if I had said it's rotating with a speed of so many radians per second, well, then we could convert v into omega, right, just by using the original equation. Also, it's a hoop, so that's one of the ones you're supposed to know. What's the rotational inertia about the central axis for a hoop? Yeah, it's just mr squared. So if we plug those two things in for omega and I, now we're getting something that looks a little bit more like the other part. So we get 1/2 times the rotational inertia of mr squared times v over r quantity squared. And again, this is the speed of the center of mass, just like the other v is. If we square this part, notice that the r squared on the bottom will cancel out with the r squared on the top. And so that leaves us with 1/2 mv squared plus 1/2 mv squared. Now you can combine the like terms. And of course you get a mv squared. Plug the numbers in, and you will get roughly 2.0 times 10 to the negative second, just to keep a couple of sig figs, joules in this case. Don't forget to square this part. Right? The units work out to be kilogram meters squared per second squared, which is a kilogram meter per second times a meter, a kilogram meter per second squared times a meter, which is a newton times a meter, which is a joule. So notice here, to find the kinetic energy, we have to break it down into rotational and translational parts, and then we can convert one to the other. Right? We can convert v into omega or omega into v, and then we can also, if we know what kind of object it is, we know its rotational inertia. That's why we're going to roll things that generally we've proven already, hoops and discs. And even though we haven't proven it, very often we use spheres, and they'll tell you the rotational inertia is part of the problem. So things that roll, nice things that roll. Part B. What percentage of that kinetic energy is rotation, and what percentage is translation? Well, this one's pretty easy. Right? If we look at this point of it before we added these two parts together, right? This was the rotational part, and this was the translational part, and you can clearly see that they're the same size. So that means 50% of it is rotation and 50% is translation. Okay? Now that's only true because it was a hoop. Right? If we go back to how we got to here, When we plug in the rotational inertia, if it's not a hoop, it's not mr squared, you're going to get some other fraction here, right on this one. And that will change how much overall of the total is rotation versus translation. So it isn't magic. It's not always 50-50. It just happens to be that way for a perfectly rolling hoop. So again, remember, rolling kinetic energy has rotational and translational terms, but you can combine them with a little clever substitution.